So we have 6 categories for radiographic variables. These are things that, if they change, may change the image. And just introducing you to them now, the upcoming lectures are going to really deeply talk about all of these sort of individually. So this first category, category 1, are called technical variables. These are things that you can, in principle, change at the control panel or on the X-ray tube that affects the image. So let's talk about each one and give a brief explanation. Electrical factors are a technical variable. These consist of milliamperage, kVp, and the type of generator you're using. Of those 3, which one can you change? Or of those 3, which can you not change? The generator, right? That would require you to get a new X-ray machine, right? Get a new X-ray generator, right? So you can change it. It's just a much harder thing to do, right? Milliamperage and kilovoltage peak, we can adjust those at our control console. Easy peasy. Milliamperage affects the quantity, how many X-rays we produce. What does kVp affect in the X-ray beam? Penetrating power of the beam, right? Let me add another way to say this. It affects the X-ray beam's energy spectrum. Okay, the range of energies in the X-ray beam. Think about it like this, right? If you set 60, if you set 60 kVp on your X-ray control console, make an exposure, the X-ray beam that you produce will have X-ray energies ranging from 0 kVp to 60 kVp and everywhere in between because of Brem's radiation. Okay. If you set 80 kVp, a higher kVp number, now your X-ray beam contains X-ray energies from 0 to 80, okay, a wider range. kVp affects the energy spectrum of the beam, but it also, as you correctly said, affects the penetrating power of the beam. A wider energy spectrum gives you an X-ray beam that's more penetrating. Good. Why is MA in here but not MAS? Why is time not included as an electrical factor? Because we usually set MAS, mass, right? But we're separating MA as an electrical factor, and we're setting exposure time as a separate thing. Why are these two not put together?
Those are both different.
They're different things, right? They're different things that affect the same thing, right? They both affect the quantity of X-rays produced. Thank you, that was good. They both affect the quantity of X-rays produced. One of them does it by changing the number of electrons we use to make X-rays, MA. The other changes quantity by just making them for longer, right? Time is time, right? How much time you made the X-rays for, how much time the exposure lasted. So that's its own technical variable. That also affects the quantity of X-rays produced. Filtration, you guys, what was the analogy we liked for filtration? What was the good, outside analogy to use for filtration? The source of energy was the sun in the analogy I used, right? And the filter was the clouds in the sky, right? The overcast day. And you guys learned from that on an overcast day, when we can't see the sun, visible light is filtered out, we get relatively more ultraviolet radiation, right? You get more sun exposure, more bad sun exposure on an overcast day when you can't see the sun than on a clear day when you can see the sun, because of the quantity of radiation you're receiving on an overcast day, more of it is ultraviolet. By quantity, more of it's ultraviolet than visible. In X-ray, we don't want the low energy stuff, okay? We would like to filter out the low energy stuff because in radiography, the low energy radiation stays in the patient, doesn't pass through the patient, and is therefore non-diagnostic. It doesn't give us any information. It just sticks in the patient and adds to their exposure. To give you a number, X-ray tubes that can operate above 70 kVp, so all X-ray tubes, require at least 2.5 millimeters of aluminum filtration. Okay, so 2.5 millimeters of aluminum filtration. I showed you guys that little aluminum coin. That coin is about 1 millimeter to 1.5 millimeters thick. So that's what's called added filtration. There is also inherent filtration built into the machine. That's what we learned, some stuff we learned about last time. Lastly, technical variable, field size limitation. Field size limitation is the size of your radiation field, right? Your collimated X-ray beam, okay? If you haven't gotten your hands on an X-ray tube and played with the collimator box yet, you will in laboratory. But setting the size of your radiation field controls how much radiation the patient receives. It also limits the amount of radiation hitting the image receptor too. So we're improving image quality and reducing patient radiation exposure. That's a really important technical variable. To give you something to grasp onto for that, your collimated field must never be larger than the size of your cassette. So if your cassette is a 10 by 12 cassette, that's the maximum size for your collimated field. It should always be smaller than that though. Category 2 are geometric variables. What do they mean, geometric variables? What would a geometric variable change? The shape of something, right? Geometry deals with shapes, right? So source to image distance, source to object distance, and object to image distance all affect shape. More accurately with these three, they affect the size of the image, but size and shape are the same, in the same category. They're geometry. So SID, SOD, OID affects size. Focal spot size affects more like sharpness. Angulation, alignment, positioning, these three, angulation, alignment, positioning, all affect shape. And we'll talk more about these in later lectures, but they affect the shape of a body part. Again, your job in some cases is to minimize shape distortion. In other cases, it might be to maximize shape distortion. And then motion. Motion just destroys image detail, right? It produces blur, right? It produces multiple images of the same object spread out over space, giving you the appearance of a blurry object. It's just like when you've taken a picture, you know, if you got a kid, right, who likes to move around a lot, like I do. I try to get a picture of her, and I can never get a still picture of her, right? One part of her body's still, and the rest is like waving her hands around. I can never get a still picture of the kid because she's moving, and the exposure times that our cameras on our phones have are relatively long, right? We could get a better picture if we had a bigger aperture and a shorter exposure time for our cameras, but we don't. We have little tiny apertures on our phone cameras, so they have to use longer exposure times. So we get motion blur. Category 3 is patient status. The patient is something to consider, right? We've talked a lot about all the other things, but we have not talked much about the patient yet, okay? So here's the way to think about this. The patient can be can be different shapes. Okay, for one, that's body habitus. There's roughly 4 different body shapes, body habiti, that we can have. They are you have the average person, we call them sthenic. You have the overweight person, we call them hypersthenic. The underweight or skinny person we call hyposthenic. And the very, very small, very, very weak person we call asthenic. We have these 4 body categories. I'm not putting them up or spelling them out because we'll get to them later. We have these 4 body categories that change the appearance of the patient, right? Larger people absorb more of the X-ray beam than smaller people. General condition, diseases, and age affect the density of their body relative to like a healthy person, okay? Usually the way we talk about this is patient status, something about the patient, is either additive or subtractive, meaning that their condition either adds density to their body or decreases the density of their body. The easiest one here is like a cast, right? A cast is an extra thing on top of or around that body part. That's an additive condition, right? It adds some density to the body, and we've got to do something to our X-ray beam to account for that added condition. Disease process example might be like a pneumothorax, a collapsed lung, okay? Air in the chest, right? There was a lung here. It has now collapsed. There is less tissue now in the way of the X-ray beam. We would call that a subtractive condition, okay? A pleural effusion, which I know I'm using technical terminology, a pleural effusion is fluid in the lungs, fluid outside the lung, but fluid in the lung cavity. And that's fluid, water, where air is normally, okay? That's an additive condition. Water where air should be is additive, okay? So we talk about patient conditions as if they, as in the context of, are they additive? Do they add density to the body? Or are they subtractive? Do they take density away from the body? Stage of respiration matters. On full expiration, a full breath out, your lungs are compressed, more dense, relatively more dense than when they're expanded. Okay. Interventional changes such as prostheses or surgical hardware, those are additive things, right? Or they might even be artifacts on the image. Like if you've ever seen someone who's had open chest surgery, they'll have literally they look like bread ties almost, right? They're wires that are connecting the sternum back together. Those are artifacts on the image now, surgical artifacts. So the patient affects things, right? And then the patient is the whole idea, right? They're the thing that we're trying to radiograph. Category 4 deals with image receptors. So whether or not you perform the radiograph on the tabletop, whether or not your cassette material is made of something that is radiolucent, as in x-rays pass through it easily, or radio opaque, which wouldn't be a good idea. Usually our cassettes are made of carbon fiber on their front face. What do we know about carbon? Anybody know anything about carbon fiber? It's light and durable, light and strong, right? And that's great for an X-ray cassette because it gets stepped on and knocked around, right? But it also has to be very, very light so X-rays can pass through it easily. Carbon is one of the lightest elements. It's 6 on the periodic table. It's one of the lightest. There's only 5 elements before it. Okay. Grids. We won't talk much about grids, but here's what you should know about grids now if you don't know anything. Grids are something put between the patient and the image receptor, and their job is to absorb scattered radiation. So one more time, placed between the patient and image receptor, their job is to absorb scattered radiation. So they're absorbing radiation from the remnant beam that doesn't carry information. When we talk about the remnant beam carrying image signal, what we didn't tell you is it also carries noise, okay? We don't really deal with TV antennas anymore, but picture the time when we did, okay? You had a TV with an antenna, and the antenna is trying to receive a signal, right? When you have FM radio is actually a good example too, right? You're listening to your radio, okay, in your car, driving here, and you drive far enough from your hometown, right? And your radio starts to get kind of go in and out, right? We're hearing clear sound, good signal. You got far enough from your radio station to now where you're getting interference, kind of crackles in the radio, not all the sounds coming through clearly. All that stuff that's not the clear sound from the music that you're trying to hear is called noise, okay? In the X-ray beam, all of the remnant beam that is the part of the remnant beam that's not carrying the information about the patient is called noise. We want to try to maximize our signal to noise ratio, okay? We want high signal, low noise, right? High noise and low signal means we don't have a good image. So we want a lot of image signal, minimal noise. Grids are a device that help us decrease noise, increase signal when body parts are especially thick. The type of receptor phosphor that you're using, this is the type of image receptor material. That matters. I won't say much more than that. But whether or not you're using CR, computed radiography, DR or indirect DR, which are both digital radiography or film screen, those affect things, okay? Roughly speaking, film shows you more detail, but less contrast resolution. You have a narrower range of shades of gray you can see, okay? DR, indirect capture DR, gives you much less image detail, but much greater contrast resolution. Many more, you can see thousands of shades of gray. By the way, your eye can only detect about 32 different shades of gray, and our radiographic systems allow us in principle to demonstrate something above 4,000, like 4,028 or something. So it's above 4,000 shades of gray in principle we can show. The computers and engineers that built these computers know that, and they don't show you all of them all at once because it's just a lot of computer processing power to do it. But in principle, your computers can show you thousands of shades of gray where you can only detect up to 32 different ones. You meaning you, but also all the radiologists who are reading the images too, right? They have human eyes like yours, okay? Um, so yeah, the computers, the range of contrast that we can demonstrate changes with our different types of image receptors, different types of phosphors, as they say. Whether or not you're using direct capture, fluoroscopic image intensifiers, or charge coupled devices and TV cameras, blah, blah, blah. These are all different ways of taking the X-ray remnant beam and converting it to a visible image. These change the way our images appear. I'm not going to go more than that into that section. This section of image processing, this is going to be the entire subject of the next module we go into, digital radiography. Okay, so just to give you some stuff here that are variables, how the image is digitized, how the image is taken from raw X-ray beam data, and an image is produced. That changes with different systems, how that's converted from image data into electronic, into magnetic, or into optical patterns for storage. Pre-processing corrections made by software. Notice this is all due with software or operator changes. Some of you are familiar with the term windowing. If you've been in an X-ray room with an X-ray tech, you probably know the term windowing. What's it mean? Seen an X-ray tech window an image? Have you seen an X-ray tech change the brightness or contrast on an image after it's produced? That's windowing. Okay, we call it window level and window width, but we usually just shorten it to call it windowing. Windowing is changing the range. So you produce an image. If it's film, there's your image. You're stuck. Okay. If it's digital, though, you can make it brighter or darker. You can make it more shades of gray, lower contrast, or less shades of gray, higher contrast. And so you can change the image after it's produced. That's windowing. That's a fantastic operation that's done. I should give you one little point of caution with windowing. When you window an image, you are taking away information from the image. Okay? Once you window and save what you've done, you've changed that image permanently. Okay? Now that information, there's less information there, meaning like the radiologist can't go back and unwindow. Okay, once you do the windowing action, it's done, and now the people who are going to go diagnose are going to have less information to work with, so you better make sure you know what you're doing if you decide to window an image, right? Taking away information is good in some circumstances, but take away too much, that's not good. If you window in the wrong way, make an image, too low contrast when it should be higher contrast, you're going to upset some radiologists or physicians, right? And that's not a good thing. Yeah.
So the program that's used where I'm working,
yeah.
There's a brightness and contrast
Yeah.
tool.
Not before the exposure, right? You're talking about the image you have on the screen?
Yeah.
Yeah.
Image
Okay.
you have on the screen. So once you take the image of the patient and even the doctors have access to that tool.
Yeah.
But it doesn't change the original.
That's really good. So in some cases with newer software, that might be the case where you save the original image data, and when you bring up the image, you make temporary changes to it, right? Soft copy changes to the image, and then they aren't saved.
Scale it up or scale it down.
Yeah. But when you take an X-ray, you produce an image, right? If you window that image and then finalize that exam and send that exam over, does the window changes you make get saved when they bring it up on their computer screens?
It's just the tool.
Okay. Most of the time, okay.
Or at least
Most of the time, once you produce an image, you look at it, you're the X-ray tech, you make some windowing changes.
Right.
Those windowing changes you make, once you click save or send, those changes get sent over. The image that they see on their computer is what you changed to.
Right.
So most of the time, the changes you make are permanent. But yeah, that's open to the different types of software to change the way that's done. So that's really good, right? Plurality of different types of software makes for different ways for this to be done. But yeah, as a general statement, what you do is permanent.
Well, windowing is basically the idea of what that is.
Brightness and contrast changes. Yep. Yeah,
I get the impression that the doctors don't fiddle with that much.
Some don't, some do. Some prefer that you don't touch it at all. Right. Some prefer that you do it do it well, so they don't have to do it, right? It's just depends. It depends, yeah. The doctors don't. In a perfect world, the physicians don't have to do anything to the image, right? They bring it up, they go, yep, there's the thing, and then they move on, right? They don't want to have to do stuff to the image. Sometimes they do, and that might help them, right? And a good X-ray tech knows what the physician is looking for, knows how to exemplify it, yeah, make it look better, right? And then show it to them. That way, there's less work for them. That's how we be good X-ray. How we are good X-ray techs. All right. Lastly, image formatting special features. These are all categories of things that are involved in image processing. We'll spend a lot of time with that in digital, so less time here. Category 6 are viewing conditions, right? Think about like when you watch a movie at home, right? You have some friends over for a movie night or something like that, right? You have your TV, it's some distance from you, right? The screen has some size. You might have even fiddled with the brightness and contrast for that TV when you set up the TV, right? The brightness and contrast on the monitor are independent of the brightness and contrast of the image that is produced from the DVD or whatever that you're watching. Said in our way, the brightness and contrast set on the monitor is a different type of thing than the brightness and contrast that you set on your radiograph, okay? Your monitors have to be set up too. Those are monitor settings, right? The ambient room lighting matters. You're at home, you want to have your movie night. Think about going to the movie theater, right? Would you have a very good movie experience if they left all the lights on? No, right? You want the lights off. Why do you want the lights off? More detail, right? You're less distracted by the lighting in the room, the ambient lighting. You watch a movie at home, you usually turn the lights off, right? Concentrate on the TV. Minimizing ambient room lighting, or if there is ambient room lighting, make it a type of room lighting that is not distracting. Peripheral lighting. My TV at home, we have this nice little LED lighting system that's behind the TV, right? It kind of illuminates behind the TV and looks nice when you're watching movies and stuff. You don't want that in a radiography suite, though. You want no distracting lighting. If you ever go into a radiologist's office, they're quiet and dark. Okay, all the lights are off in those offices, and they have 2 monitors. The monitors are really the only thing producing light in those rooms. Distracting lighting takes away from our visible information. You want adequate back illumination of the image. You want the monitor to be bright enough, not too bright. You want minimal viewing artifacts. If your computer monitor screen is literally dirty from dust and dirt, that's a viewing artifact. Minimize electronic noise. That's not a big deal nowadays. With our HDMI cables, we have minimal electronic noise. But with the old AV cables, there was always a possibility for electronic noise. If that cable kind of came loose a little bit, the video part of that cable came loose, and you dealt with electronic noise. Viewing angle, right? Go back to think about being at home with your TV and your movie night, right? Where's the prime spot on the couch? Middle, right? Your best spot is in the center. There are other spots too. Does anybody have a curved TV? You guys know about the curved televisions, right? Okay. Why are those cool?
Because at any angle you can see it.
You have a very wide viewing angle, right? People can sit at the corners of the room now and see the screen well, where they may not have been able to before, right? Like the curved gaming computers, right?
I've seen them
Really?
before and
They're a little different, harder to get used to. Yeah, I'm not I might, if I had one, be a fan of it, but seeing them, I'm not a huge fan. But but you guys understand that there's an angle that is like an optimal angle to watch TV or view your computer from, right? Some monitors, like LCD monitors, have a very limited viewing angle. Okay, so you want to consider where you're viewing the image from. Monitor brightness and contrast, monitor resolution, monitor surface reflectance. Have you ever seen a monitor that was just like hard to see the image because light was bouncing off of it so much, right? Usually that's because there's like distracting ambient lighting in the room, but monitor screens can be more or less reflective. Okay, so these are viewing conditions based on your room, your type of monitor, those type of settings. So those are our 6 categories for radiographic variables.